While an object is rolling with angular velocity omega and linear velocity v, if we were to find out the speed or magnitude of velocity of any particular point, let us say inside the object, on the rim of the object, anywhere, then following is the method to do so. So this is the speed or velocity v with which the center of mass of the object is moving, and this is the angular velocity omega with which the object is moving. Alright, so at this instant, let me take an arbitrary point. Let us say that is at an angle of 45 degree and at a distance of r by 2. So I'll show that point. Let us say this angle is 45 degree with respect to the leftward x-axis, and this distance happens to be r by 2. So what I mean to say is this particular angle is going to be 135 degree. Alright, and this distance is r by 2. So this point, let us say x, this point is going to have a velocity in this direction given by the magnitude r by 2 omega because of its rotation, and this point is also going to have a translational velocity in the horizontal direction which is equal to v. Now how do we find out the net velocity of the point x? The net velocity of the point x is simply the vector addition of the two velocities. Namely, this is the v velocity that is there in the rightward direction, and the second velocity is r by 2 omega that is in this particular direction, r by 2 omega. Now what about finding the angle? So this angle is required in order to perform vectorial addition. So this angle is simple enough to find out because this angle happens to be 90 degree and this angle happens to be 45 degree because of parallel lines. This angle is going to be 45 degree as well for this particular point. So here we see that this angle is 45 degree. So the net velocity, which is the vector addition of the two, if I complete the parallelogram, then I can draw the net final effective velocity vector to be like this, and velocity of this point x can be written, as far as magnitude is concerned, it can be written as the root of, so instead of writing root, I am writing bracket raised to half. In the bracket I get v square plus r omega by 2 the whole square plus 2v r omega by 2 cos 45 raised to half. Now physics of this question ends over here. Furthermore, according to the value of omega and v, we can actually find out the value of the magnitude of vx. Okay, right. So now let us analyze some other point apart from x. So we have analyzed this point x over here till now. So let me take a typical point, that is the point, let us say y. Now this point y is on the rim and y is moving tangentially like so. So its velocity is going to be equal to r omega in the vertical direction, that is its rotational velocity. Also y will have a tendency to move towards the right hand side because of translation. So v is the velocity of point y towards the right hand side. So as far as point y is concerned, let us say if we are to analyze point y, then in such a case we would write down directly velocity of y is going to be equal to r omega the whole square plus v square whole raised to half. So essentially this is going to be the velocity of the point y, simply speaking. Let us take, okay, and the direction of the velocity of point y is going to be like so. If in case of pure rolling, let us say the object is undergoing pure rolling, then r omega is going to be equal to v in case of pure rolling, and vy will be v squared plus v squared raised to half. So that means vy will come out to be v root 2 in case of pure rolling. So this particular situation is only in case of pure rolling. So I am writing the conditional IFF. So that means if and only if pure rolling is happening, only then this is the case. Let us say if we are taking the velocity of the highest point, let us say this point, then here r omega is also in this direction, because one can imagine that this is the radius vector r, and omega also happens to be oriented in such a manner that r omega is in this direction as well as v is in this direction also. So here the vector addition is going to be very straightforward. The angle is 0, and hence the two vectors are going to be added directly. So let us say this point happens to be the point z, let us say. Okay, now the velocity of point z can be written down as vz is equal to v plus r omega. Similarly, let us say this point is the point of contact P. So r omega is in the backward direction and v happens to be in the forward direction. So for the point of contact P, we can write down Vp is equal to v minus r omega. So similar phenomena is happening for all the points on this vertical line. On this particular vertical line, similar phenomena is happening. Okay, so we can understand that if we were to analyze, let us say, points on this vertical line, then a peculiar situation happens. We'll look at that situation in a moment. I would like to lastly analyze this particular point. Let us say this point. Let me label that point as T. So T is tangentially moving in the downward direction. So this is how it is moving in the downward direction because of r omega. And it obviously has the rightward component of velocity v. Then for the point T, similar to the point y, we are going to get the net velocity to be in this particular direction. Alright, and expression wise we'll get velocity of point T is going to be equal to, again, r omega square plus v square, because here cos theta is going to be 90 degree, so there is no point in taking the further term, which is 2 r omega v cos 90. So only this term suffices, and instead of writing the root, I am writing it raised to half. So this is the velocity of point T. Again, if and only if pure rolling is happening, then this condition will repeat and v equal to r omega will take place, and velocity of point T will be equal to v root 2, or will be equal to r omega root 2, because v is equal to r omega. So this again happens if pure rolling. Now let us look at what is happening to this particular line or points belonging to this particular line. We can understand that the topmost point is moving towards the right with velocity v plus r omega. the bottommost point is moving towards the right with velocity v minus r omega. So if r omega is actually greater than v, then the bottommost point is actually moving towards the left, also called as backward skidding or backward slipping. If v is greater than r omega, then the point P, point of contact P, is moving forward, and that is called as forward skidding basically. Alright, so let us analyze. I'll take a situation wherein firstly I'll assume v to be greater than r omega. Now we know that the velocity of the center is only v, because the center is not rotating, because all the points are rotating with respect to the center. So the omega that we are writing down is with respect to the center. So the center is stationary with respect to itself. It is not rotating. That is what is assumed in physics always. The velocity of this particular point, let us say, is v minus r omega. So a small velocity in the rightward direction is present. So this is v minus r omega. And the velocity of this particular point happens to be equal to v plus r omega. Alright, so we'll draw a large value. So this will come out to be v plus r omega. Now an interesting fact that happens is as follows. Velocity of all the intermittent points, let us say all the points that are lying on this particular line. So velocity of all these intermittent points Alright, so velocity of all these intermittent points is going to be linearly proportional to these three values of velocity. Or even if two values are given, that also would have sufficed, but I have drawn three values over here. Now what do I mean by that? So what it means is, let us say if we join this particular line like so, then velocity of any given point is going to be in magnitude from, let us say this point is given, its velocity is going to be this much. If this point is given, its velocity is going to be this much. If this point is given, its velocity is going to be this much. So this can be found out and verified. So this is how the velocities of all these points would behave. So this is the velocity profile of this line, essentially, as this line is rotating. And finally the last point will have a velocity v minus r omega. So the velocity will linearly scale from v plus r omega to v minus r omega. That is what will happen over here. Now, if let us say instead of v being greater than r omega, we were operating under the case that v is less than r omega, then in that particular situation, what would have happened is as follows. Let us say if v was less than r omega, in that particular situation, the bottommost point would actually be moving towards the left. So that means that at the bottommost point, I would have had to write this velocity and say that the magnitude of this velocity happens to be equal to r omega minus v, because now we are operating under the condition that r omega is greater than v. So the magnitude of this velocity is going to be equal to r omega minus v. Alright, so the magnitude of the velocity of the topmost point remains actually as it is. It is going to be equal to v plus r omega. Now as far as this straight line is concerned, let me write down this to be equal to v plus r omega. So now as far as this vertical straight line is concerned, we have to analyze what is happening for all the points on this vertical straight line. Okay, so the same thing is going to happen, just with a small difference, that we have to join these 2 points in order to find the velocity profile. So essentially, this particular point that we are getting, this is a point wherein the translational and the rotational tendencies are cancelling out, essentially. Alright, and for all other points, what is happening? Let us say for this point, the velocity is going to be like so, like earlier discussed. So this can be said to be the velocity profile diagram for all the points lying on this vertical straight line. So mind you, all these are instantaneous velocities, like so. Then again, for this point the velocity is 0, and since v is greater than r omega, for points that are near the bottommost point, they will actually have a tendency to move backwards because backward slipping is happening. Just like in the previous case, the bottom points had a tendency to move in the forward direction. So this is the velocity profile diagram. So the student of physics and a student who is good with rotational motion should be familiar with how the velocity profile varies with respect to vertical line of an object having circular cross section, that is rolling, meaning undergoing rotational and translational motion simultaneously.